For today's geometry video, we will be using in class 9 for standard 3. So if you don't have that yet, go ahead and find it. The introduction has us use a triangle. So I have a triangle here available, and the instructions tell us that we are supposed to cut or rip off each corner. So I'm going to do some labeling here just so that it's a little bit easier to see on the recording. This is going to be angle number 1. And then up top, this corner is going to be angle number 2. And then the third corner of this triangle down here, I'm going to label as angle number 3, just so that I don't lose track. So the goal is going to be to rip off each of these corners and to investigate what's true. I'm actually just going to rip off 2 of them. I'm going to leave this one attached to the triangle. And so it says to place the 3 corners together so that they all share the same vertex. So if I'm looking at angle 1, the vertex would be right there, that corner where the 2 sides of the triangle come together. Angle 3, the vertex is in the corner, so I'm going to line that up. And then angle 2, the vertex right there, line that up. And then it says, what do you notice? And so if we pay attention to what's happening here, when those 3 corners of the triangle are lined up, do you see how nice and straight that side becomes? It's a little bit tricky to show, but there's this nice straight line here. And so if we think about these 3 angles combining together, if they're making that nice straight line like we know about from standard 2, that's going to be kind of like our linear pair theorem, except it's not a pair of angles, it's actually a trio. And so it looks to me like we have our first big idea, which is probably something you already notice, but those 3 angles form a straight angle or a straight line. And that will tell us what they add up to be. So if we remember from our linear pair theorem, the sum is going to be 180 degrees when that happens. And so our first big takeaway is called the triangle sum theorem, and that tells us exactly that fact. The 3 interior angles of a triangle always add up to 180 degrees. So it wasn't that the triangle that I started with today was special. That's just a fact that's true for all angles in all triangles. So if we pop back up to these examples, we should be able to probably answer each one of these using that idea. So if we're looking for the measure of angle A, that would be this corner right here on the inside of triangle ABC. We know these 2 angles are 48 and 42. So if I were to take the measure of angle A and add it to 42 and add it to 48, that total would be 180 degrees, thanks to the triangle sum theorem. These 2 add up to be 90 if we're combining like terms, and so the measure of angle A actually turns out to be 90 degrees. 180 minus 90 is 90. Moving on to example B, they want us to find the measure of angle DFE. So if we start at D, we trace to F, and then we bend back towards E, we're looking for this angle right here. So again, that's an interior angle for triangle DFE. So if we want that measure, I'm going to use a question mark just to shorten that up a little bit. That angle plus 31 plus 126 must total to be 180 degrees. If you go ahead and combine those like terms and then subtract, we're going to turn out with 23 degrees for the measure of angle DFE. We've got one more of these, so let's take a look at angle GIH. GIH. Sure enough, that's an interior angle again. We have the other 2 angles given to us. So that angle plus 55 plus 78 will total up to be 180 degrees. Thanks to our triangle sum theorem. And if we add those and then subtract them over to the other side, that angle will be 47 degrees. So one of the things that we can do is we can use the triangle sum theorem to find a missing angle anytime we know 2. So we need to know 2 angles, and then we can find the third angle using that theorem. We can also, now that we have some values, start to do what's called classifying. So classifying triangles can happen based on their sides and also based on their angles. So what we're going to focus on as part of in class 9 is how to classify triangles based on angles. And then when we move to in class 10, we'll learn how to classify based on sides. So an acute triangle is going to be a triangle that has 3 acute angles. Try to test yourself and see if you can remember what acute means. Equiangular is going to be a triangle that has 3 equal angles. But if the angles are all 3 equal, we know the total is 180. So we can divide that by 3 and figure out that they're actually always going to be exactly 60 degrees when we're dealing with an equiangular triangle. A right triangle is going to be a triangle that has exactly 1 right angle. That means there's going to be a 90-degree angle, or we'll see that little box in the corner of an angle that indicates that it's a right angle. And then an obtuse triangle is going to be a triangle that has 1 obtuse angle. So hopefully you remember acute is going to be a measure between 0 and 90. Obtuse is going to be a measure between 90 and 180 degrees. So if we pop back up to our 3 examples at the top, A, B, and C, we're going to classify these now based on what we know about the angles. So we have 48, 42, and 90. It almost seems like it was going to be an acute triangle because these are both acute angles, but that 90-degree angle means that it's actually a right triangle. It has 1 right angle, 1 90-degree angle. This one over here, we wouldn't have even needed to solve for the missing angle. This 126-degree angle is obtuse, and all it takes is 1 obtuse angle for us to have an obtuse triangle. And then last but not least, if we look at example C, the angles are 78, 55, and 47. All 3 of those are less than 90 degrees, so this would be an acute triangle. All right, so triangle sum theorem is going to help us solve problems, and then we're also going to be asked to classify triangles by angles as part of our work. There is a second theorem that we're going to use as well, but in order to use this theorem or understand it, we need to have a definition to help us out before we start. So the definition is going to be what an exterior angle of a triangle is considered to be. So our definition tells us what it looks like. An exterior angle is going to be an angle that forms a linear pair with an interior angle of the triangle. So if I pick an interior angle, let's say this one at the top of the triangle, there are actually 2 options for an exterior angle at that location. I could swing out this way and find an exterior angle because these 2 angles form a linear pair, exterior angle, or I could swing out this way and find an exterior angle because again, these 2 angles form that nice straight line. So no matter which corner of the triangle I'm at, there are going to be 2 options for exterior angles. So the 2 options here would be these 2. They would be exterior angles to this interior angle. Or the last option, this angle here or that angle there would be exterior angles for this interior angle right inside that triangle. So when we're thinking about the exterior angle theorem, we're going to come up with something new that's true. The linear pair theorem tells us what's true about these 2 angles, interior and exterior, that are adjacent. But we're going to come up with something new that we can say about the triangle and the exterior angles as well. So here we go. The exterior angle of a triangle is going to equal the sum, remember sum is a clue about an addition problem, of the 2 non-adjacent interior angles. Now that's a slightly complicated idea, so we're going to use this picture to help it make a little bit more sense. In this picture, where is the exterior angle? Well, that's going to have to be this one right here because that's outside the triangle. So the exterior angle comes first in the theorem. It's going to come first in the equation as well. So we're going to talk about how the measure of angle MNP, that's the exterior one, is equal to, so we've got our equal sign, the sum, so there's our plus sign, and then the two parts of that sum are going to be those non-adjacent, that means not next to, but still interior angles. So this angle right here would be the adjacent one. We do not want that one. We want the others. So the measure of angle P would be an important one to include in the sum. It's not adjacent, but it's interior. And then the measure of angle O would be the second part of that sum, not adjacent to the angle on the exterior, but inside that triangle. And the reason that works is because these three interior angles have to add up to be 180, and these two angles also have to be able to add up to be 180. So we're doing a substitution. If you want to see more about that proof, you could probably YouTube it and find one, or you can follow up with your teacher in class and they'll explain a little bit more about why that fact is true. Okay, we're moving into using this knowledge now. So down at the bottom of the front side still, we have some practice with finding some missing angles as well as classifying by angles. So this would be a good opportunity for you to pause the video, try these three problems, and then press play and see if you've done those problems correctly. Okay, let's see how you did. For this first example, you should have ended up with the measure of angle A equal to 40 degrees. We got that from adding the three angles together to be 180 and then subtracting 99 and 41. The most important angle to notice in this triangle is that 99-degree angle from the measure of B. That tells us this is an obtuse triangle because that angle has a measure larger than 90. For number 2, your answer for the measure of angle C should be 42 degrees. That again comes from adding up to be 180 and then subtracting. There was a right angle in this problem, so we had to know that that was 90 degrees thanks to that little box, which also means that this is a right triangle when we're classifying by angles. And then last, number 3, the measure of angle C is 55 degrees. Again, that comes from the three interior angles needing to add up to be 180. Then these three angles all turn out to be less than 90. So that means this is going to be an acute triangle. All right, flip the page over and meet me back here for some examples. For your in Class 9 examples, we're going to continue to use these ideas, but in situations that are a little bit more complicated. So when we look at this problem, example number 4, there are actually two angles they're asking us to find the measure of, angle 1 and angle 2 in this top corner. But there are actually multiple triangles in this picture that we might focus on to help us make that happen. I think the best place to start is actually by finding the measure of angle 2, because if I look at this triangle here, I see a 90-degree angle in the corner and a 27-degree angle in another interior spot. So that means that the measure of angle 2 could be found by adding those three angles together to be equal to 180. So if we go ahead and subtract the 90 and the 27, or we add them first and then subtract, the measure of angle 2 should turn out to be 63 degrees. We don't have to do this, but if we were classifying just that part of the picture, that triangle would be a right triangle, thanks to that 90-degree angle. To find angle 1, we have to think a little bit more creatively. So if we focus in on that part of the picture, this triangle over here, it looks like we really only have one of our angles labeled, the 76, but I'm noticing right here a linear pair from standard 2, two angles that are adjacent that form a straight line. And so even though I don't have to find this angle, Subtracting 90 from 180 and filling this one in as 90 degrees as well will help me to track down my angle 1 measure. So the measure of angle 1 plus 76 plus 90, again, cover all three interior angles, and so they have to add up to be 180 degrees. Once we get that solved for, the measure of angle 1 will be 14 degrees. So that would be another right angle. Next up we have example 5, which is going to be similar to the problem that we just did in example 4, except that there's only one triangle available. We still know the three interior angles though, so our triangle sum theorem tells us that 68 degrees, the measure of angle B, plus 2x, the measure of angle C, plus 3x minus 3, which is the measure of angle A, all must add together to be 180 degrees. If we combine some like terms, both the variables and the constants, then when we solve, we should be able to get 5x equal to 115. And then dividing both of the sides of that equation by 5, x turns out to be 23. And there's a little bit more to do for this problem because they also ask us to find the measure of angle A, and they ask us to classify this triangle by angles. So not only do we need to take angle A and replace that x with 23 to figure out its measure, I believe that's going to turn out to be 66 degrees, but also we need to take a look at all three angles to try to decide what kind of triangle this is to classify. 68 and 66 are both acute angles. We should double check just to make sure we know what that third angle is before we make our decision. Since that turns out to be 46 degrees, we're now officially dealing with an acute triangle because all three angles are less than 90 degrees. Taking a look at number 6, the type of problem changes. So this problem has what we call that exterior angle. And although there are lots of ways we can solve this problem, since there's an exterior angle, I'm going to go ahead and use the exterior angle theorem, which means I'm not going to focus on angle 3 right here. That would be a linear pair. We'll come back and find that one later. But I'm going to focus on those two angles that are non-adjacent to my exterior angle and use the theorem which tells me my exterior angle is equal to the sum of those two non-adjacent interiors. So 124 subtract 49 will give me 75 degrees for the measure of angle 1. Now there are a couple of options about how we can finish this problem. We could use the triangle sum theorem to find angle 3. 75, 49, and the measure of angle 3 have to add up to be 180. Or we could use our linear pair theorem from standard 2. Either way, once we do that calculation, I'm using linear pair theorem, so I did the measure of angle 3 plus 124 equals to 180. Subtract that 124. Angle 3 should turn out to be 56 degrees. This one also asks us to classify triangle ABC by angles, so we aren't going to pay attention to that exterior angle. That one doesn't matter. We're looking at the three interior angles, so 75 degrees, 49 degrees, and 56 degrees. Again, those are all three less than 90 degrees, so this is a second acute triangle. Moving to example number 7. We're asked to solve for x, and we see that little double-sided arrow, so that tells us the algebra might be a little bit tricky. That angle, again, is another exterior angle. So we know the measure of that exterior angle is going to equal the sum of the two non-adjacent, so not the one down there at C, but the other two interior angles added together. Since this equation only has x squared and it doesn't have x to the first power in it as well, I'm going to leave x squared on the left side of the equation by itself, move all of the numbers over to the other side, because this is going to be a situation where solving by square roots is possible, which means that in algebra, we could have positive 6 or negative 6. Now in geometry, those answers don't always both work. So if we pop back up to where the x is located, positive 6 squared plus 22 would work out to be 58, which makes sense. That's what 18 plus 40 equals, so that all checks out. And if we'd pop negative 6 in there and substitute it, negative 6 squared is also positive 36, which when you add 22 to it also turns out to be 58. So both the positive and the negative answer work for this geometry problem. One more round of classifying here, but again, remember that exterior angle doesn't matter. It's the interior angles that we need to look at. And one of those is missing. So we have 18 and 40, which are both acute, but we shouldn't make our call on what kind of a triangle this is by angles until we know that third angle. It certainly looks obtuse, but looks are not going to be what we want to rely on either. So I'm going to quickly solve for what that last angle should be. You could do that by using the triangle sum theorem with the 3 angles inside, or you could do linear pair theorem with that 58-degree angle we just found. Either way, that angle is going to turn out to be 122, I believe, but I'm going to double check that arithmetic. Yep, 122 degrees. And so it does turn out to be an obtuse triangle right there, but we want to make sure that we're not making that decision based on how the picture looks, but instead based on the actual angle measures once we find them. On to question number 8. I see one more chance for us to practice that exterior angle theorem. 5x plus 30 is the angle on the exterior of the triangle. And so that's going to equal these other two non-adjacent interior angles added together. There are some like terms to combine on this side. Be especially careful with those two negative 10s. 4x and 3x add together to be 7x. Negative 10 minus 10 more is negative 20. So then I'm going to subtract 5x and add 20 to get me to the point where x is going to be 25. To classify, though, I need to know the angle measures inside the triangle. So I'm going to substitute in and see how large this top angle turns out to be first. 4 times 25 is 100, minus 10 is 90. I got lucky there. If that's exactly 90 degrees, I don't need to substitute and find these other two angles because I know that that triangle is going to be a right triangle when I classify it based on its angles. If that had been an obtuse angle, same thing. It's an obtuse triangle automatically. But if that had been an acute angle, something less than 90, I'd want to plug in to this other expression to see what's true about that angle's measure, as well as find this angle over here to see if those are also acute or if something else happens in one of those two locations. Last but not least, one more chance to practice some algebra. I'm seeing 3 interior angles here. So those 3 interior angles are all going to be added up together to equal 180 degrees, thanks to my triangle sum theorem. I purposely listed the x squared first because I know I want that to be listed first and stay positive. Then I see positive 3x, and then I have some like terms to combine as well as 180 to subtract so that my equation can be equal to 0. That's going to be important for this one because I can't square root like I did in example 7. This is going to be a factoring problem. So whatever your process for factoring, we're looking for things that multiply to be equal to negative 70. And those same two numbers need to add up to be equal to positive 3. So if we go through factors of negative 70, 1 and 70 won't work, 2 and 35 won't work, 3 and 4 don't divide evenly, 5 and nope, that's not going to work, 6, 7, 7. There we go. If we make this negative 7 times positive 10, that will multiply to be negative 70, but negative 7 plus positive 10 will add to be positive 3. So my factors will look like x minus 7 and x plus 10. Set those both equal to 0 to find our possible algebra answers. And x turns out to be 7 or negative 10. If I take the 7 back to the picture, 3 times 7 is 21. Sorry for that interruption. 21 plus 29. So that seems to work out. 7 squared would be 49. So those all seem like reasonable values. So x equals 7. Angle P they're asking me for. So if x is equal to 7, that means angle P would be equal to 50 degrees. Oops, not 51, 50. If I take negative 10 and I plug it in, negative 30 plus 29 is not going to give me a geometric answer that makes sense because that would be negative degrees. So I'm just going to get one answer for x and then one answer for the measure of angle P. Again, that's 50, not 51. All right, thanks for watching. We'll see you back in class.